In the configurator .NET file, we have a simulated network consisting of hosts, routers, switches, and a special component called IPv for network configuration, the configurator. This configurator is responsible for assigning IP addresses and generating routing tables, making the network function efficiently without requiring manually configuration. The network structure follows a realistic model. Hosts act as standard computers. Routers handle packet forwarding and routing decisions. Switches serve as intermediary devices connecting hosts and routers. Connections are structured as follows. Hosts connect to switches. Switches link to routers. Routers interconnect to enable communication across network segments. One notable aspect of this setup is the link speed. Most connections run at 100 megabytes, but the link between router 0 and router 2 is only 10 megabytes, which affects routing decisions later in the simulation. Now moving to configurator A, this file controls how the network behaves. At the start, logging settings like configurator dump addresses equal true allow us to see assigned IPs, networks, topology, and routing tables during the simulation. The configuration follows a step-by-step approach. Initially, IP addresses are automatically assigned. Later, some IP are manually set. Then IP assignment follows a substructure, making the network more scalable. In the step 4, static routing tables are generated, meaning each device knows exactly where to forward packets. To test this, a ping request from host 1 to host 7 verifies connectivity. As the configuration progresses, routing rules are refined, first automatically, then manually. Routing is optimized further when link speeds are taken into account. Faster connections are preferred over slower ones. Eventually, wireless communication is introduced, replacing Ethernet connections step by step until the entire network runs wirelessly. Automatic static routing. At this stage, the IPv4 network configurator automatically generates static routing tables. Routers determine the best paths for data transmission, ensuring that packets are forwarded efficiently. To validate the setup, a ping request is sent from host 1 to host 7. If routing is configured correctly, the ping should succeed, meaning the device can communicate properly. This step reflects how real-world networks operate. where routing tables allow data to flow seamlessly without manual intervention. Routing based on link speed. Now routing decisions are no longer arbitrary. The system considers data rate when determining the best path for packets. For example, the 10 megabytes link between router 0 and router 2 is significantly slower than the 100 megabytes connections elsewhere. As a result, traffic will avoid router 2 unless necessary, ensuring faster and more efficient data transfer. This approach mirrors real-world networking, where traffic naturally prioritizes high-speed links to optimize performance. Manually defining routing costs. Instead of relying on automatic link speed prioritization, we now manually assign costs to different routes. By adjusting these costs, we can influence routing behavior. For example, we might instantaneously make a certain path more expensive, forcing the network to choose a different route. This technique is crucial in traffic engineering and network optimization, as it helps balance load distribution, prevent congestion, and improve overall efficiency.